Okay, now that we've learned how to do the end behavior or find the end behavior of a polynomial, we want to move into some other aspects of polynomials, because remember, the end goal for us today is to be able to graph a polynomial by hand without our calculator. So in example 5, we're going to find the zeros of this polynomial algebraically, and so I'm going to start off by just taking the polynomial and setting it equal to 0. That's how I would find the zeros of a function. And notice that every term here has an x in it. And so what I'm going to do is start by factoring out that greatest common factor of x, and that's going to leave me with x squared minus x minus 6 is equal to 0. Now, looking on the inside of the parentheses, I'm left with a quadratic that has 3 terms. And so I need to be able to know how to factor this. Since the leading coefficient there is a 1, I'm going to be able to skip some work here. And so all I really need to do is figure out factors that will multiply to -6, which is the constant term here, and add to -1, which is the b coefficient in front of the x term. And so what two factors will multiply to -6 and add to -1? Well, that's going to be some combination of 3 and 2, and in order to add to a negative number, the 3 is going to have to be negative. And so I've got my parentheses that's going to factor into x minus 3 and x plus 2, and so therefore I'm going to be able to find my 3 answers. So setting the first factor equal to 0, setting the second factor equal to 0 gives x equals to 3, and the third factor equal to 0 gives x is equal to -2. Okay, letter B, again, if we want to find the zeros, the first step is to set the function equal to 0 and try to solve. And just like on letter A, I see that I have a greatest common factor of an x, which I can factor out, and that's going to leave me with x squared minus 49. Now, in the parentheses, I don't have 3 terms like I did in A. I have 2 terms that are being, that is a difference of one another, and notice that both of the terms are perfect squares, and so therefore this is going to factor as a difference of squares. The x will just carry down, and I'll have x plus 7 multiplied by x minus 7. And so therefore, 3 answers. X is equal to 0, which comes from this factor right there. X is equal to -7, which comes from that factor, and then x is equal to +7, which comes from that third factor. So a third degree polynomial led to 3 answers. Okay, one other thing that's going to be helpful for graphing polynomials is to know what a multiplicity is and what that determines about the graph at that particular 0. So really important definition here. If f is a polynomial function and x minus c raised to the m power is a factor of f. And so if you just take a look down at the example number 6 here, this is essentially what I'm talking about. Here would be x minus c raised to the m power. So here c would be 3 and m would also be 3. In this particular factor, c would be -2 because you see x plus 2 here, and then m would be 2. M, the multiplicity, is essentially just the exponent on that particular factor. Now, any 0 that has a multiplicity of 2 or more is what we call a repeated 0 or repeated root. And you can really use either word interchangeably there. Repeated 0, repeated root. Any 0 with a multiplicity of 2 or bigger is called a repeated root. And so here in example 6, I want you to find the zeros and state the multiplicity. So if you take a look at this first factor, x minus 3, what number for x is going to make that equal to 0? And hopefully you said x is equal to 3. But that 0 occurs more than one time. In fact, it occurs with a multiplicity of 3. And the way that I got that is I just took a look at the exponent that was on that particular factor. Now, my other 0 comes from the second factor here, x plus 2, and x plus 2, setting that equal to 0, is going to give me a value of -2, but that 0 occurs more than once. In fact, it occurs twice. It has a multiplicity of 2 because of the exponent that is on that particular factor. So 2 zeros, but they both occur more than once. And so what actually ends up happening is that you have 5 zeros. It's just that they're repeated, if that makes sense. So you have 1 0, x equals 3, that's repeated 3 times. Another distinct or unique 0, x equals -2, that occurs twice. And so the actual degree of this polynomial is actually 5, and you don't need to multiply all of that out to know that. All you really need to know in order to know the degree is what the multiplicities are, and then if you add the multiplicities up, that will tell you what the degree of the polynomial is. Okay, so if you were learning about multiplicities and wondering why is that important, I'm really glad that you asked, because that is right here in my notes. And so why is the multiplicity important? Because it tells us the behavior of the graph at each particular 0. And so here's what I mean by that. If a polynomial function that has a real 0, c, has odd multiplicity, then the graph of f crosses the x-axis at that point, and the value of c actually changes signs at x is equal to c, either from positive to negative or negative to positive. So basically what the graph is going to do is it's either going to go from being above the x-axis to below, or from below the x-axis to above the x-axis whenever you have an odd multiplicity. So maybe a picture would help. If I have an odd multiplicity, this means that the graph is actually going to cross at that particular x value. So let's just say that I have a polynomial that looks like x plus 2 raised to the 3rd power, which would have an odd multiplicity. In that particular case, I'm going to have a 0 here at -2, and the graph is actually going to cross the x-axis at -2. And more specifically, it's going to cross the x-axis like a cubic function does. And so what I mean by that is it's going to sort of flatten out and not just cross straight through, but actually kind of flatten out at that particular 0. And so notice what happens here. The graph changes signs. It goes from negative, being below the x-axis, to being positive or above the x-axis at that particular 0. And it's important that you can see a graph and identify that quickly, that the graph changes signs from negative to positive or from positive to negative, whatever the case may be. Now, what if the multiplicity is even? Well, that's where the second sentence comes in. The second sentence up here says that if a polynomial function has a real 0 of even multiplicity, then the graph of f bounces off the x-axis at that 0, and the value of f does not change sign at x is equal to c. So bounces off, you can see I put it in quotes there. That's sort of an informal way to say this. Another way would be to say that the graph of f is tangent to the x-axis. So you might hear me use that terminology as well. And so what does it mean if we have an even multiplicity? It means that the graph is tangent to the x-axis. And so a really good example of this would just be y is equal to x squared. And so y is equal to x squared equals 0 at x is equal to 0. And then what happens at 0? Well, the graph comes down, it touches or bounces off of that 0, and then bounces back up. And so notice what's happening to the graph. It is not changing signs at that 0. To the left of that 0, the graph is above the x-axis or positive, and to the right of that 0, the graph stays positive or above the x-axis. So we do not have a change in the sign of the function at that particular 0 whenever the multiplicity on that 0 is even. So hopefully that's making sense to you. Hopefully the pictures are helping, and we'll work a couple of examples where we graph where multiplicity and whether it's odd or even will become very important in our graphing. Okay, so we're going to put everything together here in example 7 and graph this polynomial by hand. And so we're going to talk about degree, we're going to talk about end behavior, we're going to talk about zeros and multiplicities, and be able to put all of that together in order to sketch a nice graph by hand without our calculator. So let's start with the zeros, because that's just sort of the logical place to start whenever we have a polynomial. So if you look at the first factor, x plus 2, that's going to equal 0 whenever x is equal to -2. Now, it also has a multiplicity. Remember that multiplicity is the exponent on that factor. That's a multiplicity of 3, which of course is an odd number, which means that the graph that we draw is going to need to cross through the x-axis at that particular 0. So keep all of that in mind when we go to graph, that odd multiplicities means the graph is going to cross through the x-axis at that 0. My other 0, looking at the second factor, is going to be x is equal to +1. That's going to have a multiplicity of 2 because of the exponent on that particular factor, which means that we are going to have an even multiplicity, and the graph is going to be tangent to the x-axis at that particular 0. Now, when you do the degree, all you really have to do when you find the degree of a polynomial is add up the multiplicities of the zeros. And so if we have a multiplicity of 3 and a multiplicity of 2, adding those together tells me that the degree of my polynomial is going to be 5. And I don't have to multiply it all out in order to know that. If you were to think about it, x times x would give me x to the third, and then x times x would give me x squared, and when I multiply x cubed times x squared, I'm going to get x to the fifth. Now, I'm also going to be able to see pretty easily here that my lead coefficient is going to be 1, and more specifically, positive. And why does that matter if my lead coefficient is positive and my degree is odd? Because it tells me what my end behavior is. And so that's the other thing that I'm going to write down here is the end behavior, and I'm going to do it in limit notation. And so the limit as x goes to -infinity of this function, f of x is equal to, and then I'll just go ahead and write the other limit statement over here, and we'll talk about what it is. And so odd and positive means what? It means that it's going to go down to the left and up to the right. And so this left end behavior is going to be -infinity. The right end behavior is going to be +infinity. And so this is all of the information for this polynomial. And now I want to try to use all of that to sketch an accurate graph. And so here's my attempt at an accurate graph. I'm going to start with my zeros, which are going to be -2, and over here at +1. My end behavior, I know, is down and up. So I'm just going to draw little arrows at the ends here that show this graph going down and up. And there's one more point that I'm going to use in order to sketch an accurate graph, and that's the y-intercept. And so remember, back to section 1.3, how do we find the y-intercept of a graph? We let x be 0. And so I'm just going to evaluate f of 0 here, and that's going to be 0 plus 2 cubed times 0 minus 1 squared, and that is going to equal to 8. And so I'm just going to very carefully here, up at 8, put a y-intercept. And so let's now fill in the middle parts of this function by paying close attention to our zeros, their multiplicities, and whether or not we should cross or just go up and touch and bounce off the x-axis. So starting over here on the left, I know that the first place I'm going to go is this 0 right here. And then if I look back at my information over here at x equals -2, I said I was actually going to cross the x-axis. And I'm going to do it like a graph with multiplicity 3 does. And so that's going to look like a cubic. And so really, probably what I need to do is actually erase a little bit of this and come into this 0 more like a cubic does, where it sort of flattens out. And notice that I'm actually crossing the x-axis there. Now, the next place I'm going to go is up to this Y-intercept, and I'm going to go through that, and then come back down to this next 0. Now, what am I going to do at that 0? Well, take a look back at your information. At x equals 1, we said we were going to be tangent to the x-axis or bounce off of the x-axis. So I'm going to come down and touch and then bounce back up, and that's perfect because that leads me to my right end behavior, which said I had to go back up. So in red, I'm going to draw the wrong way to do it. If I were to cross through that x-axis erroneously or in error, then notice in order to go back up to my end behavior, I would actually have to cross through the x-axis somewhere, and that would give me another 0 right there that I don't have. And so that's how you know the red is not correct. And so you want to make sure that you're paying attention to those things as you are drawing your sketch. Okay, in letter B, we want to do all the same things that we just did in letter A, just a different problem to give you some more practice. So first of all, what are the zeros? Well, take a look at that first factor and you get x is equal to 1. And hopefully you're catching on to the multiplicity being the exponent on that factor, multiplicity of 3, which of course is odd, which means that we are going to cross through the x-axis at that particular 0 like a cubic would, meaning it's going to flatten out just like I showed you on the previous example. My other 0 is going to be x is equal to -2. That's going to have a multiplicity of 2, and that is, of course, even, which means that the graph will be tangent to the x-axis at that particular 0. The degree of this polynomial is just the sum of the multiplicities, which is going to be 5. The lead coefficient, again, is going to be 1, which, of course, is a positive number. This is an odd degree, and so therefore, this, again, is going to be down and up in our end behavior. And so if we write our end behavior limits, we have limit as x goes to -infinity of f of x. That's going to equal to -infinity. And the limit as x goes to +infinity of f of x is going to be +infinity. Now, the last thing is the y-intercept. Remember, that was a helpful thing to give us a truly accurate graph. And so to find the y-intercept, I know I'm going to plug in 0 for x, which is going to be -1 cubed multiplied by 2 squared. -1 cubed is negative, and then 2 squared is 4. So my y-intercept is going to be -4. So if I get ready to draw my graph here, I know that I'm going to have a 0 at +1 and a 0 at -2. The end behavior is going to be down on the left and up on the right, and I'm going to have a y-intercept at -4. Okay, so I'm ready to start over here on the left with my end behavior that goes down. I'm going to draw my function going up to my first 0 right there at -2, and looking back at my information at -2, I said I was going to be tangent to the x-axis, which is good news because if I were to cross through the x-axis, how in the world would I be able to get back to this y-intercept? I would have to go back through the x-axis somewhere here in order to get there, but I can't do that because I don't have a 0 there. And so hopefully that discussion is sort of making sense to you. I'm sort of trying to build you up to something that we're going to do in the future, but hopefully you understand why we have to be tangent here, not only based on the multiplicity, but also just on the common sense of what the graph needs to do in order to go through the points that I've drawn. So I'm going to bounce off of that. I'm going to come back to my y-intercept here, and then what am I going to do at that next 0? At x equals 1, I'm going to cross, and I'm going to cross like it is a cubic. And so I'm going to come up, I'm going to flatten out just slightly as I come through that 0. I'm going to go up and then approach my right end behavior.